Welcome to Pre-Calculus. Today we will investigate function composition, focusing on whether or not function composition is commutative. Let's take a look at two examples that involve equations and then two examples that involve numbers. Our first function composition is here with two functions, f of t equals negative 3t plus 4 and g of t equals 3t minus 5. So we've got two function compositions to perform. The first direction is f of g of t. Just so we can see what that means, we can write this in a separate way. This is equivalent to f of g of t. And those two expressions, the one that was given originally and the one that's rewritten here, are equivalent. So I want to compose the g function within the f function. So what I'll do is I'll take the f function, which is the overarching one, and I'm going to write it, but where I reach the variable t, instead of writing t, I'm going to leave an open space. And then I'm going to complete the f function by adding 4. Now, to compose the function, I'm going to take all of g of t, so 3t minus 5, and I'm going to substitute that in where there was just t in the original f of t. So one thing that we can think about in terms of domain and range is that when I'm composing a function inside of another, I'm taking the range of one function and substituting it in for the old domain of the original. Once we made that substitution, we want to simplify. So I see that I need to distribute negative 3 through the parentheses. And that's going to give me negative 3 times 3t is negative 9t. And then the second distribution, negative 3 times negative 5 is plus 15. And then I'll add 4. And to complete that simplification, I'll just add my constant. So this is negative 9t, and then 15 plus 4 is 19. Negative 9t plus 19. So that is the equivalent of f of g of t. Now we do want to check to see whether or not function composition commutes. In other words, can I switch the order and get the same result? Well, let's try it with this second instruction. So the second instruction is the other order. And what we'll do is we'll write it again in the equivalent way. So this is really g of f of t. And this second way of writing it lets us see that really I'm taking all of the f function and I'm substituting it in for the variable in the g function. Let's make that substitution. So for this example, I'm going to take the g function is the overarching function, so 3, but when I reach t, I'm going to leave a space. That's where the f function will substitute in, and then finalize this linear minus 5. I'm going to take the f function and I'm going to make that composition. So where there was just t and g, I'm now going to place all of the f of t, negative 3t plus 4. So again, we want to simplify. We are on the lookout for whether this is also going to reduce down to negative 9t plus 19. Let's distribute this positive 3, double distribution there. So this would give me 3 times negative 3t, negative 9t. 3 times 4 is positive 12. And then I'll tack on minus 5. And although my variable term looks the same, both of these start negative 9t. 12 minus 5 is 7, and that does not equal the output when I did the other direction. And so from a first view, we see that function composition is not commutative. These two expressions are not equal. Well, these are two linear functions. So we've seen that composition is not commutative. if I'm dealing with just two ordinary linear functions. We'll write that because it's kind of the conclusion we're making here is that it's not commutative. Well, let's take a look at some other types of functions, see if the case changes. So here I've got, again, two functions. F of x, again, is linear, no change there. G of x is a polynomial, x cubed plus 2x squared. So our first direction is the same. I want to calculate f of g of x. To help visualize that, again, I'm going to record it in this alternative method. And then let's make the composition. So now I'm going to take the f function and leave a space for the g function, and then subtract 1. I'm now going to substitute in g of x where I had the variable x in the original f of x. So this is going to become x cubed plus 2x squared. And that's ready to simplify again by distributing that constant, or that coefficient 3. That's going to give me 3x cubed plus 3 times 2x squared is going to give me 6x squared minus 1. So the first direction of that composition yields another polynomial, a cubic function. So again, we're interested in whether this is commutative. Can I switch the order and get the same value? So for my next direction, I'm again going to start with the other function g of x and compose in f of x as the new domain. Let's see how that composes. Let me get those functions in view. So I've got two occurrences of x and g of x. So I've got to put f right in both those spots. So I'll leave a space where x was to the power of 3 plus 2, and then leave a space where x was the second occurrence squared. Substitute in the f function. So it's going to appear twice, 3x minus 1 and 3x minus 1. And that gives us some work to do algebraically. So I need to expand these cubes in this square. So let's get to work with that. Just so we can kind of visualize what's going on. This literally is 3x minus 1 times itself 3 times. So we'll expand that. And then also plus 2 times 3x minus 1 times itself twice. This gives us opportunity to practice our double distribution. Another name for double distribution is the FOIL method. So the F stands for first terms. I'll go ahead and record that acronym, first terms. So that's going to give me 3x times 3x is 9x squared. O stands for outer terms. 3x times negative 1 is going to give me minus 3x. I stands for inner terms. My inner terms here are going to be negative 1 times 3x. Those happen to be the same because these are identical binomials. And then the L, as you can probably guess, are the last terms. In this case, negative 1 times negative 1. And that'll be positive 1. I'm going to put that third 3x minus 1, and then I'm going to record this 3x minus 1 times 3x minus 1 in that second grouping is going to be the same because those are the same two multiplications. So I'm just going to record again 9x squared minus 3x plus 1. So on this first set of terms, I need to distribute a second time Because notice I've got this quadratic times the linear 3x minus 1. I do want to reduce my work, and I also want to switch it around. So I'm going to move that 3x minus 1 over to the left, just to make for ease of distribution, times 9x squared. Notice I can combine these inner and outer terms. They're the same like terms, same over here. So negative 3x minus 3x, that's going to give us minus 6x plus 1. So I will write that here as well. 9x squared minus 6x plus 1. So now I'm ready to finalize the second round of distribution. FOIL works when I got two binomials. The idea with distribution, though, is that each term goes to each term. So I'm going to have to do this manually without an acronym for this, because this second one is a trinomial, but that's okay. So that's got our multiplying bars shown, the little arches. 3x times 9x squared is 27x cubed. Second one is 3x times negative 6x, that's minus 18x squared. And then 3x times 1 is positive 3x. We're now going to distribute negative 1 to each term in the trinomial. And I'm going to record the values underneath the term that they would combine with from my first distribution. So negative 1 times 9x squared is negative 9x squared. Notice I'm lining up the x squared terms. Negative 1 times negative 6x is plus 6x. I'm lining up the linear terms. Negative 1 times positive 1 minus 1. I also want to distribute this constant 2 through that second trinomial. So this becomes plus 2 times 9x squared is 18x squared. 2 times negative 6x, negative 12x. 2 times 1 is positive 2. So all the distributing is complete. What I need to do now is finalize combining like terms. So now I've got 27x cubed. Negative 18x squared minus 9x squared is going to give me negative 27x squared. 3x plus 6x plus 9x minus 1. And then I'm going to take the terms of this second trinomial and record them underneath the terms they'll combine with for the final polynomial. So I'll put 18x squared under negative 27x squared. Under 9x, I'll write minus 12x. And then under minus 1, I'll write plus 2. And that will give me my final polynomial. So we've got 27x cubed. And then negative 27x squared plus 18x squared is going to give us minus 9x squared. 9x minus 12x is minus 3x, and negative 1 plus 2 is plus 1. And that is complete. So that shows the second direction of the multiplying. And when we compare again our two directions, we see very clearly that these two f of g of x and g of f of x, they're not the same, not equal. So again, we conclude here that function composition is not necessarily commutative. Thank you for joining for this first segment of composing functions. We'll come back in a moment to compose functions involving a number. Here we've involved variables. Thank you for joining. See you soon.